Hi, this is Ms. Fitzmaurice, and this video is an explanation of how to solve 2D conservation of momentum problems. Okay, so in this video, first I'm going to have you remember how to do 1D momentum problems. I think in general, most of you guys need a little more practice with that. Then I'm going to show you how to use the 2D momentum equations, and then you're going to try an example from your packet. Okay, so the first thing we're going to do is you should get out your textbook, and I want you to turn to page 188 and read through problem 4. Okay, spend a couple minutes, try to do it by yourself, and then check back for the solution. Alright, so number 4 says, a child in a boat throws a 6.4 kilogram package out horizontally with a speed of 10 meters per second. Okay, it wants you to calculate the velocity of the boat immediately after, assuming it was initially at rest. It says the mass of the child is 26 kilograms and the boat is 45 kilograms. Okay, so because we have two objects interacting, this is going to be conservation of momentum. Since it says ignore water resistance, we can say there's no no total outside force on the system, and so momentum should be conserved. So we're going to draw a before picture and an after picture. Okay, in this situation, the person is just sitting in the boat. They have the package. Okay, nothing's moving, and so the total momentum, sigma p naught, is going to be equal to 0. Okay, afterwards, we have the person is in the boat, and they threw their package. We know that they threw their package with a velocity of 10 meters per second. Okay, so that's something like 16 miles per hour. That's pretty reasonable. And we want to know what is the boat's final speed. Okay, so we can set up our conservation of momentum equation. Sigma p naught equals sigma p. If you haven't already set it up, go ahead and try to do it for yourself. Alright, and so now that you have tried that, at the beginning, as we noted, nothing's moving, so there's no momentum at all. We just have 0. And then at the end, I have the mass of the package, velocity package, plus the mass of the boat plus the person. And I'm just going to say that's m boat person times b boat person. This is not dividing by, it's just that the boat and the person move together. Okay, so at the end of the day, I'm looking for this number. And because the package is moving to my right, boat of the person are moving to the left, I expect this to be a negative number. Okay, so I can go ahead and I plug in the numbers I have. I have 0 is equal to the mass of the package times velocity of the package, so that's 6.4 times 10, plus the combined mass of the boat and person, which is 26 plus 45 times v boat person. Okay, so obviously this multiplied together will be 64, and I'm going to subtract 64 from both sides to get negative 64 is equal to, when I combine 26 and 45, I end up with 71, so negative 64 is equal to 71 times v boat person. Okay, I'm going to divide both sides by 71, and I end up with the velocity of the boat and the person is equal to negative 0.90 meters per second. Alright, so just quickly what we did is we drew a before and after picture, filled in Newton's second law, and then we went ahead and solved. Okay, so now let's talk about what should happen in two-dimensional momentum problems. So in 2D momentum problems, we have objects moving in two dimensions. Okay, so a classic example, and I'm pretty sure this is what your book uses, is say you had pool balls. So I have, say, a red ball, and maybe it's heading in this direction, and I have a blue ball, and it's just sitting there, but the red ball hits the blue ball kind of not straight on. So there's some kind of collision between them. The red ball hits the blue ball. Maybe because it's not hit it straight on, the blue ball is moving sort of this way and the red ball is moving this way. Okay, so things are not moving straight in one line. They're moving both up and down and side to side, or sort of, you know, this way and this way. Okay, now just like we did in kinematics and just like we did in forces, for momentum we can use the conservation of momentum equation in two dimensions. All we have to do is put a little x under everything. So we have sigma p naught x equals sigma px. That means all the side-to-side momentum is equal to all the side-to-side momentum, whether it's at the beginning or the end. And then we also have sigma p naught y equals sigma py. Okay, and obviously you can't break a mass into x and y, but the x part of a momentum will be mass times the x part of the velocity. The y part of a momentum is equal to mass times the y part of a velocity. Okay, and then the total momentum of a single object, and we draw this with a little funny hat over its head because it's a vector, will be basically the hypotenuse, you know, of those two things, or the total momentum. So that would be vx squared plus vy squared square rooted, or we could say to the 1/2 power. Alright, so basically the way you solve two-dimensional momentum problems is exactly the way you solve one-dimensional momentum problems. The only difference is that you write out two equations instead of one. You still draw a before and after picture. You still try to plug in your masses and velocities. Okay, so now let's... Alright, so in our first example, let's think about two objects. They could be two cars. One is 1,500 kilograms, and it's moving to the right, or we could even draw cardinality and say to the east at 10 meters per second. The other object, another car, is moving 25 meters per second to the south. Okay. Now my question is, if these two cars collide, okay, and they stick together in their collision, so they kind of crumple and stick together, how fast will they be moving at the beginning? Or sorry, at the end? And compared to east, what angle will they be moving? Okay, so these are our before and after pictures. Remember, what you have to do is you still write sigma p naught equals sigma p, except now you're going to do it in 2 dimensions. So we have sigma p naught x equals sigma px. So all the side-to-side momentum at the beginning equals all the side-to-side momentum at the end. And we also have sigma p naught y equals sigma py. So all the up and down momentum at the beginning equals all the up and down momentum at the end. Okay, so I'm going to give these guys names. I'm going to call this A and this B. And so at the beginning, in the x direction, okay, I'm really saying it's mass A times V naught AX plus MB V naught BX. Okay, so that's what's going on in the beginning. And I see that B is not moving from side to side at the beginning, so this goes away. And that is equal to, they kind of move together as one object, MA plus MB together times the final x velocity. Okay, and basically I'm just putting in, this is P final. Remember that momentum is mass times velocity, but since they're moving at the same speed, I just combined their masses. Okay, so that's what's happening in the x direction. In the y direction, I have at the beginning MA VO AY. Okay, so the velocity of object A in the y direction. Notice that A is only moving to the side and not up and down, so this will be 0. Plus MB VOBY, okay, which we see is 25. And that's equal to, again, their combined masses, so it's MA plus MB times the final velocity, so in the y direction. Okay, I can pretty easily now put in numbers and solve for Vx and Vy. Okay, so that's what I want to do next. I'm going to put in what I know. MA is 1500, VOAX is 10, and that is equal to my combined masses, so 1500 plus 600 is 2100 times Vx. Okay, I can pretty easily divide both sides by 2100, and I end up with Vx is equal to about 7.14 meters per second. Okay, now in the y direction, I can fill in my numbers. I'm going to make a little more space in the y direction. I have MB, which is 600, times VB naught y, which is 25, and that's equal to the combined mass. Again, that is 2100 times Vy. Again, I can pretty easily solve for Vy, and I end up with Vy is equal to 7.14 meters per second as well. Okay, if you've been watching closely, you may have realized I made one mistake. Okay, VB naught y is actually going to be negative 25. So we have a negative in here, and our Vy will also be negative. Okay, so remember, what I'm really going after, and I'm going to go to the next page, so make sure you have everything down, is total velocity and my angle. Okay, so to find my total velocity, remember I have 7.4 and negative 7.14. What I have to do is I have to use SOHCAHTOA. Okay, so I have 7.14 meters per second, that's my Vx, and negative 7.14 is my Vy. And remember that my total velocity will be the hypotenuse of these two. Okay, so what I want you to do is go ahead and take a minute, use the Pythagorean theorem, and find me what this guy should be. Okay, and when you use the Pythagorean theorem, you find that your total velocity is about 10.1 meters per second. Okay, now if we want to know the angle, I'm going to look at this angle right here, and what we can do is we can use inverse tangent, unless you realize right away by looking at this what angle we should have, but we can use tan theta is equal to opposite over adjacent. Okay, and in this case we have 7.14 over 7.14. So we have tan theta is equal to 1. We take the inverse of both sides, so we have tan negative 1 of tan theta, and that just gives us theta. And then we have tan negative 1 of 1, and we end up with theta is equal to 45 degrees. Okay, and then remember that when we're specifying direction, we say 45 degrees something of something else. Okay, so in order to get this angle, we started in the eastward direction, and then we kind of rotated downward south, so east to south. And so the way we write this is kind of backwards. It's 45 degrees south of east. Alright, so hopefully this has given you a basic idea of how to solve two-dimensional conservation of momentum problems. Again, it's pretty much the same as doing it in one dimension. You just put an x and a y at the bottom of your velocity. Alright, so the last thing we're going to talk about is we're going to kind of expand on this idea. You've seen in pretty much every topic we've covered that you can put an x and a y on a bottom. Okay, so my next question is, what about impulse? And really, are there any equations where we're not going to be able to put an x and a y on the bottom? The answer is that we can break pretty much everything I'm going to say every quantity that is a vector remember that vector just means it has both a size and direction into x and y. So as long as your equation is an equation that contains a quantity that you can break up into x and y, and that's the basis of your equation, then you can do that. Okay, so for example, you can do that with impulse. You can write jx equals m delta vx, and jy equals m delta vy. You can write fx delta t is equal to m delta vx. You can write fy delta t is equal to m delta vy. Okay, so pretty much any equation you can write as both an x and a y, and the more formal way to do it, instead of writing out an x and a y every time, is to give your letter that is a vector this hat. Okay, so this little arrow thing, and we actually in physics we call it a hat. So J is equal to mv, and there's an arrow on the J, and then there's an arrow on the V, and it's really a half arrow. If you think it's kind of like a sideways symbol for those electron configuration diagrams you had to draw in chemistry last year. Okay, and you can write F delta T equals M delta V. Okay, similarly you can write sigma P naught with a hat equals sigma P. Alright, so hopefully this was helpful, and I will see you tomorrow. Actually, Wednesday, not tomorrow.